Hello, welcome back. In this lesson, we're going to implement the SPI config function. This is the function that would configure the SPI module. So I'll say void over here, SPI1 underscore config over here, and takes no argument. Open and close over here like this. So we're going to start off by enabling clock access. We created a symbolic name here called SPI1EN. We're going to use that to enable clock access to the SPI1 module. We do that by setting this bit 12 in the APB2 enable register to 1, just like this. Okay, so once that is done, we're going to set the clock of the SPI module. To do that, we need to analyze the SPI control register 1. So I'm going to come to our reference manual over here and search SPI underscore CR1. Okay, it requires me to say, let's see, I typed SP. Okay, SPI CR1. Okay, let's see. So SPI CR1 here has a number of bits. Okay, so bit 3, 4, 5 here are known as the BR. Let's take a look at what they are used for. So we use this to configure the baud rate. Right, so we simply want to put a value that we want to divide the SPI clock by. Remember, the default frequency of our microcontroller is 16 megahertz without changing anything. The default frequency of the STM32F411 microcontroller is 16 megahertz, and this is the same frequency that goes through the various buses without any prescaler. So then this means the frequency of the APB2 bus, which the SPI is connected to, is also 16 megahertz. So what we're going to do is we're going to slow that down a bit. We're going to divide the clock by, say, 4. I'm going to divide it by 4 over here. So I'm going to set PCLK. PCLK stands for peripheral clock. And the peripheral clock is basically the clock of the bus that the peripheral is connected to. In our case, it's the APB2 bus, which is 16 megahertz. So we're going to set 16 megahertz divided by 4 here. And to do that, we have to set the first bit to 1, the second bit to 0, the third bit to 0. And let's see, BR. So we have to set bit 3 to 1, bit 4 to 0, bit 5 to 0. Okay, that's what we're going to do. And this will give us PCLK divided by 4. Okay, very simple, very straightforward, like this. Okay. Next, we're going to set the clock polarity to 1 and the clock phase to 1. To do that, we still need to check the SPI control register 1. So there is the C pole and C far over here. Okay. So over here, we can simply do that by setting bit 0 to 1 and bit 1 to 1 as well. But I'll leave it up to you to create symbolic names for these bits. I'll just go ahead to set bit 0 to 1, bit 1 to 1. Very simple, very straightforward. Next, we're going to enable full duplex. So let's check our control register 1 and find the bit that is responsible for that. Bit number 10 over here, let's inspect it. It's called the RX only bit. Okay, it says when this is 0, full duplex is enabled. When it is 1, it is in receive only mode. So I'm going to enable this by setting it to 0. Next, we're going to set the MSB to be first. And we still remain in the control register. In fact, all of our configuration will be done in the control register 1. So let's see. So bit number 7 is called the LSB first. Let's inspect it. So if this is set to 0, MSB is first. And if this is set to 1, LSB is first. So we're going to set it to 0. So we simply disable bit number 7 like this. Next, we're going to set the SPI to be in master mode, because our microcontroller is the master and the accelerometer device is the slave. So I'm going to come over here, scroll up to find the bit responsible for this. Okay, bit number 2 is called master. Let's see what we need to do to bit number 2. I'll scroll down here. It says if it is 0, this is slave configuration. If it is 1, it is master configuration. So I'm going to set it to 1 as it says over here. Next, we're going to set the data size, whether we want 8-bit mode or what. So to do that, we go back to control register 1, our favorite register for this lesson. Let's scroll up. Bit 11 here is called a DFF. This is the data frame. Let's see what that has got to say. Data frame format. If we want 8-bit mode, we've got to set this to 0. If we want 16-bit mode, we've got to set this to 1. So we said we want 8-bit mode, so we want to set this to 0. So we disable bit 11. Okay, so next we're going to configure our SPI to work in software slave management. And this implies that we have to set the SSI bit to 1 and then SSM bit to 1 as well. Let's find these bits in the control register. So let's see. This is the SSM bit. So this is bit number 9. And this is the SSI bit number 8. So let's see them. So it says this is the software slave management. When 0, software slave management is disabled. When 1, software slave management is enabled. So we want to set this to 1. And SSI here is internal slave select. This bit has an effect only when SSM bit is set. The value of this bit is forced onto the NSS pin, and the IO value is, and the IO value of the NSS pin is ignored. So we're going to set this to 1 and set internal slave select. Okay. Like this. Okay. Next, we're going to enable the SPI module. So let's see the SPI control register for the last time. Okay, bit number 6 here is the SPI E, meaning SPI enable. And as you can guess, it says this disables the peripheral when it's 0. When it's 1, the peripheral is enabled. So we're going to set bit number 6 to 1 to enable the SPI. So we're looking good. So this is it. In the next lesson, we shall implement the functions to receive and to transmit data using the SPI module. We'll conclude this lesson here. I'll see you later.